This one is large.
Good morning, folks. So, first of all, I want to apologize for the somewhat grumpy Piazza post from 2 nights ago. As I said, changing the rules on the fly is not a good idea, and I won't do it. I'll answer questions about homework too. And secondly, but it did. The grumpy post ended up being useful in the sense that there was some really good feedback from students about ways of doing this, and I'm going to adopt one of them, and that is that homeworks from now on, not homework 2, but homework 3, will be due for everyone Sunday night before the lab starts at midnight. So homework 3 will be due on the 24th of September, which is a Sunday, at 23:59. The huge advantage of that is that Monday morning, then I can go over the problem set, talk about the solutions in time for lab on Tuesday. Any questions about that? Any comment about that? 23:59, Sunday night, September 24. Homework 3. Furthermore, this also does another thing, and that is it separates the due date for the homework from the due date for the lab report. So they're not both due at the beginning of the lab. The second aspect is that the lab report will then be due at midnight the night before your lab section. So both deadlines are being changed. So homework 3 will be due on the 24th of September for everyone. And lab 2 write-up, which you're not going to start for another week and a half or so, will be due at 23:59 the night before your lab section. This decouples it from lab. It allows you to think a little bit more about the lab and a little less about the lab report in the hours leading up to the lab. So I think it's a good separation. Is that a hand up or is that just scratch? Okay.
Does that mean that we don't have to hand in a physical copy of the lab report?
Physical copy of the lab report is up to your TA. It turns out that some TAs are paper bound. They like to edit on paper. I like to edit on paper. I hate trying to mark up electronic stuff. I want to be able to scratch all over it with my red pen. But other TAs prefer electronic. It will be up to your TA, but you must hand in an electronic copy time-stamped by midnight of the night before. Any other comment? I'll modify the timing chart on the website in the next day or two. I haven't done that yet. No real change in workload, just a little change in timing. And I think for good reason. Separating the deadlines is a good thing, and making the homework due at a uniform time is a good thing because it makes the system fairer, I think. Any comments? Any more comments? Questions? I added a couple of sentences to Lab 2, so you might want to reload on your browser. One is that there's a nice clean example of the keyboard on the development board page. which includes connections, assuming that you're using the big board. And the output from this lab is going to be through speakers. And I realized that probably when you look at an audio plug, there's 3 contacts on it, which you can all see, I'm sure, from there. There's 3 contacts. Well, it turns out those contacts have names, of course. They are called the sleeve, the ring, and the tip, and the ground is always the sleeve. It's the outermost conductor throughout the cable because it acts as a shield. And our speakers are wired exactly this way, the only difference being that the body of the plug is green and not black. And I have a box full of sockets that allow you to plug in, and there's 3 wires on the bottom, ground, left, and right. Ground is always the outer conductor. So one way of figuring out which ground is on this connector is to take the ohm meter, touch the ground connection, which has got to be the outer conductor, and you'll find that this pin, the center pin, is connected to ground, and the other 2 are left and right, and I can't remember which is which, but it doesn't matter because you're generating mono anyway. So probably what you're going to do, rather than try and plug this thing into the whiteboard, it will plug in, but it tends to pop out if you breathe hard on it. So what you're going to want to do instead is to solder a wire to the ground pin and a wire to both of the left and right channel so you can wire it over to your board. Just regular old solder, just regular old hookup wire. Any questions on that? Any questions about lab 2? Everybody got keypad working? How many people got keypad working? So that's any problems with that? Any recommendations? It just worked. That's good. Yes?
What's a good way of testing that your debouncing circuit is actually working the way you want it to be?
Well, so how do you test a debouncing circuit? What you could do is make a display on your TFT so that the first time you press, you have a number. Then the second time you press, you have a number. The third time you press, you have a number. The fourth time, the fifth time, across the screen, and then press the sequence, and if you get each one exactly once, your debounce is working. If you press the 1 and you get 1, 1, 1, it's not working. If you press and you get nothing, it's not working. Now, that's a rather high level test. You might also want to, during debugging, slow down the state machine, which is running at about 30 hertz, slow down the state machine and print the states out. Print the state name. To make sure that when you press, it goes through the states you expect, and when you release, it goes through the states you expect. Audio synthesis. How many people got audio? It can make a tone. Some people got tones. Is anybody finished? I saw a couple of people that were close. Okay. Any other questions on lab 2?
Can I ask you a question about homework, Joe?
Sure.
So what would the effects of different types of amplitude modulation be on the sound you hear?
So the main difference is if you merely turn on the sine wave and turn it off, then that is equivalent to multiplying a sine wave that goes on forever times a square wave of unit amplitude with this duration. And if you Fourier transform the product of those, you will find that the high frequency edge implied by a fast rise time here appears in the spectrum as a square wave spectrum, modulating the sine wave spectrum. So that you, and the acoustic effect is that you will get a loud click. And the shorter the burst, the more obvious the click will be, because the more energy is carried by these fast edges at the beginning and end of the pulse. Once you get away from a square wave, once you get away from the square wave, the artifact, the click artifact, is highly suppressed. The question number 4 is what kind of amplitude modulation will you use and why, is partly how in the hell are you going to generate it? All right, so a cosine, a raised cosine, sort of like a Hamming window, is going to be hard to do because I'm asking you for a precision duration. Okay, where exactly is this thing on versus off? At what amplitude is it on versus what amplitude is it off? With a linear rise and a fall, you could say, oh, it goes from half amplitude to half amplitude. You could do that here too. You could say half amplitude to half amplitude, but the center of the call would be louder. Maybe that matters, maybe it doesn't. Another possibility would say, okay, let's make the system as smooth as possible. Let's make the system as smooth as possible and do a half cosine rise, swap over to a horizontal line, and then do a half cosine fall. That's very smooth because all of the derivatives are continuous and therefore the spectrum is as compact as possible. Or you could do a Gaussian rise and a Gaussian fall, which would be even more compact. But how are you going to generate the cosine in real time? How would you do that? You'd have to use direct digital synthesis for the modulation as well as the sine wave. You have to do a table lookup for the rise and the fall. The fact is that the click suppression, the MATLAB program which is linked here, will show you that the click suppression for a linear rise is pretty good. So this is not only a theoretical question, why would you use it in the mathematical sense, it's why would you use it practically? What are you going to generate and how? Everything's a trade-off. Sine is easy to generate and pretty good. Cosine rise and fall is harder to generate and is slightly better in terms of spectrum. So you have a quality versus pain trade-off. As I said last week, from my point of view, linear rise is good enough. There'll be a few purists who can't take the discontinuity in the first derivative. That's okay. I appreciate that personality construct. But as I said last week, it's good enough. So really this is, how are you going to generate the linear ramp? I want you to think about the timing. I want you to think about the thread. Oh, wait a minute. Maybe you can't put the modulation in a thread. It's got to be in the interrupt service routine. Oh, so you have to generate modulation in interrupt service routine. These are the kind of questions I want you to think about when you answer question 4. What is the practical aspect of the generation? Is that enough? What else? Anything else?
Could you possibly go over the example code you have online for the DAC?
Sure.
The accumulation and the phase adding.
So you're talking about this example. In which there's you're talking about the interrupt service routine here, right?
Right.
Okay, so this interrupt service routine is triggered on a timer interrupt, which in my code I believe is running at 100 kilohertz. Let's just check that. It's running, as I said, at 200 kilohertz. Yes, you're quite right, it's 200 kilohertz. And where's that ISR? Okay, so now what are you asking about, the phase accumulator?
Yeah, well, just basically what this code kind of walks through it.
Okay, what this code is doing is running a direct digital synthesis sine wave generator and a serial peripheral interface DAC driver. So think of the phase accumulator. So the phase accumulator is the phasor which generates the sine wave. Remember that phasor, word phasor from all those years ago? It's a rotating something or other that rotates through phase space and generates a sine as a projection on one of the axes, in this case the imaginary axis. So what we're doing with the phase accumulator is saying we're going to set it to some angle and then we're going to step it by delta theta, and delta theta, so phase accumulator is theta and delta theta is the increment, is the phase increment. So we're stepping this phasor around a unit circle until it overflows back to 0. And the overflow back to 0 in the code is mediated by the overflow of a 32-bit number back to 0. So the topology of counting of an overflowing counter is the same as the topology of counting of a phasor circulating, all right? So the phase accumulator here is getting the phase of the sine wave. Once you have the phase, you look up in a table, you got the value of the sine. So the next step is then a sine table lookup according to the top 8 bits of the phase accumulator. Why the top 8 bits? $256 samples on a sine wave is enough on one cycle of a sine wave. 256 cycles per sine wave cycle is enough to get the distortion down, 2 orders of magnitude or so. Who ran that case through the MATLAB code? Anybody? 256 samples on a, I don't remember what the answer is. A couple of orders of magnitude of signal to noise ratio. So it's enough samples. So usually the next question is, if you're only using the top 8 bits, why do you use a 32-bit counter? Is that clear why? Is it clear why? You can think of all of the other bits, top 8 bits, you can think of all these bits down here as being on the other side of a binary point. That's supposed to be 8, not infinity. Sometimes write sideways on the board. You can think of this as a binary point where this is the index number of the array, and all of these bits are fractional indices. They're the fractional index. And by having a lot of bits down here, you're allowed to accumulate a lot of fraction before you click over to the next full index, which means you can go to a very low frequency. In fact, with 32 bits sampling at 100 kilohertz, I think you can get down to like 10 to the minus 10 hertz. There are pi times 10 to the 7th seconds in a year, within 0.1% or so. So 10 to the minus 10 hertz is long. Long is defined as longer than it takes to get tenure. There's academic jokes, yeah. So does that answer your question, or does it just merely perplexify it?
It helps,
But what seems to be the hang-up?
like, okay, you have the DDS, you have accumulation, but what does that help you? Like,
It's getting the phase angle of the sine wave you want to output. And it changes linearly in time. So updating it is easy because it's a steady increment. You're updating the phase angle continuously in time by a uniform amount, because that's how you generate a sine wave from a phasor, is you uniformly sweep the phase angle in time. Because it is a uniform increment, I can just add a constant, so it's easy. And then the value of the sine table is directly related to the phase angle. In fact, it's unique with the phase angle. You buying that? Does it make sense? The thing about this algorithm is it's too simple. There's something about it that seems too simple, but it works very well. The huge advantage in terms of calculation is that the frequency output is exactly proportional to the increment. You double the increment, you double the frequency. And so calculating, going from a given frequency to a increment for doing the calculation is as straightforward as plugging into this formula, which F out and the phase increment are linearly related by some constant that we talked about a week ago or so. Yes?
Why do you check in your ISR time?
Oh, up in the when I was writing this code, I was interested in how long it took this code to execute. And so by reading the ISR time, I could tell how long it was from the time the hardware event occurred, which zeroed the timer, which is what throws the interrupt flag, right?
you get 74 cycles, right?
74 cycles to get into the interrupt. The rest of this interrupt only takes like a dozen cycles. So it takes longer to get into the interrupt and out of the interrupt than it does to actually compute this interrupt.
It's like the vector table is like that.
The vector table only takes, so
How is it saving, basically?
it's saving 32 registers, and it takes 2 cycles per push to push the stack. So there's 64 cycles right there. It's saving some other registers besides the general purpose registers. You could turn that off by using, if you look at the ISR macro definition, you will find that there are some keywords that you can use to cause only the registers that are used to be stored rather than all of the registers. You can change the level of optimization from 0 to 1 in the compiler control, in the project control. That helps. because optimization level 1 will actually check which registers are used. And if you're completely crazy, you can rewrite this all in assembler, and then you don't have to save anything except the registers you use, and then you can push those onto the stack yourself. I highly don't recommend that. Okay, so once you've got the value of the sine wave, then we have to convert it into a form for the DAC to use. And we have to config channel A. There's the control bits that come from the definition of the chip, which I explained before. You take the DAC data. The DAC data was the sine wave table is defined from plus 2048 to minus 2048, and we need to change that to offset binary 0 to 4096 for the DAC internal representation. So we're adding 2048 here. That offsets the 0 value of the sine wave. So the 0 value of the sine wave is now at value 2048. The minimum is at 0 and the max is at 4096. So we start the transaction to the DAC by clearing the chip select. We do the SPI write, which loads the SPI transmit register. As soon as you load the SPI transmit register, the SPI hardware barfs out the bits, in this case at, I believe, 20 megahertz. Spits out the bits. You don't spit out the bits, the hardware does. You wait for it to be done, and when it's done, you set the chip select high again to end the transaction. When you set it high, bink, the voltage appears on the DAC. That's the signal to the DAC to spit a voltage out onto the terminal. In fact, the wire is called DAC, DAC output A. So this is sort of a minimum stanza for outputting a value onto the serial peripheral interface bus. Anything else in here? Yes?
Can I ask a question about something? I think it's a name for the DDS example. Maybe I might be wrong, but it's somewhere in one of your examples. It's like the comment is this improves ISR performance, and then you clear a bit in some port. Does that sound familiar?
No, I'm sorry.
Can you scroll down a little bit more? I think
It's in the wild, right?
no, it's not here.
I don't think it's here.
I'll just.
Yeah, tell me where to go.
I thought it was,
No, don't do that. Okay. Yes.
I'll completely different question.
Yeah.
Why not modulate amplitude in the thread?
Why not amplitude modulate in the thread? So the minimum delay on a thread is about a millisecond. And you're going to have to update the modulation amplitude more often than once per millisecond. Now you can figure out a way, we talked about this, you can make the delay on a thread be less than a millisecond. If you use PT delay, if you do PT yield time milliseconds, the minimum number you can put into this call is 1. This is an integer that goes in there. However, underneath that call is a timer 5, ticking away at, I think it's 40 megahertz. You can read that timer directly and get the number of ticks, and you can wait for a certain number of ticks of the microsecond timer and go faster than a millisecond. You can make a wait time shorter than a millisecond. I have not implemented that. I have not tested it. but it'll work.
Turn into like yield time up till timer.
You do a PT yield until timer greater than timer plus X, right? My feeling is that doing the syllable start timing in a thread makes sense. So you say syllable start, the interrupt pops awake and produces the modulation envelope and stops again and waits for the next start. So you might break up the effort here by putting by starting a syllable, by setting a flag, and then the interrupt service routine generates the envelope, runs open loop until it gets to the end, turns off and waits for the next start flag. That puts the high speed stuff in the interrupt and the low speed stuff in a thread.
So the way that it's supposed to turn off is that you press a button on the keypad and then it turns off.
So this is going to stop making sound at the end of every syllable and then start again, right? And so I'm talking here about the syllable timing, but yes, you should be able to kill the entire thing by pressing the stop button or start a song by pressing the start button, yes. That state machine, that start-stop state machine, and all of the millisecond timing is better done in a thread because there's certain structures you really should not put in an interrupt service routine, like a while loop. Really bad idea. Yes?
So if you get the stop command from the keypad in the middle of a syllable, should it
Well, so let's say that the silly human presses the stop button right here. What should it do? What should it do?
Finish the syllable and stop.
One strategy would say finish the syllable and stop. That would be a click avoidance strategy. On the other hand, I haven't specified what it should do. And so really what's going to happen is, well, I mean, the easiest thing to do would be to wait for the state machine to fall through again. Notice there's going to be some timer going off with some state machine analyzing the input parameters and the keyboard and who knows what else, and say, oh, person stopped it, stop now. My guess is, so then you get down to the psychophysical effect of what constitutes simultaneity. What is the longest time that you can go between a button push and a result and your brain thinks it's happening at the same time? Guess?
200 milliseconds.
200 milliseconds. Okay. Well, any other guesses? This is a different question than how short an interval can you could detect, or how phase relationship between two sounds. And it turns out 200 milliseconds is just about right, because it takes almost 200 milliseconds for a perception to become a conscious event. This raises serious psychological problems of how anybody can drive a car, but certainly 100 milliseconds is good enough. You're running the key scan state machine at 30 milliseconds. That suggests that putting the entire state machine in the key scan state machine is reasonable. You're going to interpret that as you pushed a button and it went off, and with no perceptible delay. What else? Generally, the specifications for the lab have some loose ends. I'm not trying to tie everything up. If something isn't specified, then you're free to interpret it in a reasonable way. Where reasonable is determined by what? By TA, I guess. So if you see a loose end, chat about it. Do we need to be able to input decimal durations? No. You're inputting milliseconds. That's the only that's all the resolution you need. Do we need to interpret decimal frequencies? No. So so every number you enter from the keypad will be an integer between 1 or maybe 0 and 10,000. So 4 digits. Let me say again, I gave you a table here of 4 calls of actual crickets. It is not sufficient to press the 0 and have call 1 play. That is not what I'm asking for. What I'm asking for is that you be able to set the entire range between 10 and 1,000 milliseconds, between 1 and 100 milliseconds, and between 1,000 and 6,000 hertz. So you have to have completely general integer input up to 6,000.
But I understand that part, but would you also like a presets?
If you want to put in presets, that is fine. Yes, you do not have to.
Well, it's necessary to have the user input a number for each.
You have to input a number for each of 5 parameters for any given song. Now, you could say, well, I only want to change one parameter. I want to change it from a kilohertz to 2 kilohertz. So it seems like a reasonable user interface would allow you to choose one of 5 and change that, rather than having to input all 5 for every song. What else? All time intervals and burst duration accuracy should be plus or minus 1 millisecond. That is explicitly because I want you to be able to use the millisecond timer in PT threads.
How do we test frequency accuracy? Just scope.
Well, you have a test button that when you press it puts out a tone continuously, and you're going to put that on the oscilloscope and measure the frequency, yes. So you can do it, there's 2 ways. One is in the lower right corner in a little tiny 6-point font, it gives you the frequency to 4 places or 5 places. That's really handy. The other possibility is you could put the oscilloscope in FFT mode. You'll see a sharp peak. You should see a sharp peak at the frequency of your sine wave. You freeze it, dial the cursor over to it, get the frequency. That'll only give you about between 2.5 and 3 places, which, by the way, is good enough for 1% accuracy. Barely.
Maybe the tone, do you have to ramp up to the tone, or do you?
For test mode, nah, you ram the button down, it comes on full power. The point of the test mode is to make a constant sine wave that's long enough for the oscilloscope to do the analysis. So it doesn't have to be debounced, it doesn't have to be ramped up and ramped down. If it clicks a little bit at the beginning, neither you nor the sine wave or the oscilloscope are going to notice it.
Okay, so you can use that to test a specific frequency, but what do you have to modulate across the whole range in order to make sure that you get every frequency correct?
Oh. So the TA is probably going to test 1 or 2 frequencies between 1,000 and 6,000. TA could say enter 1250 hertz, and it should be within 1% of 1250. So you're going to choose one sample rate, and you're going to synthesize all of the sine waves at one sample rate. So once you get the first frequency right, they should all be on within 1%. Right. Should take no extra calibration, because you are locking everything to the CPU clock. And by the way, how accurate is the internal PIC32 oscillator? What kind of a question is that? Is that a datasheet question, a hardware manual question, or a PLIB question? What document are you going to find that in? The what? Datasheet. Datasheet, yeah. It's only 350 pages. But there's a reasonably good search term here. It is now the middle of Lab 2, which means it's time to start talking about Lab 3. And we only have a couple of minutes. I'm just going to talk a little bit about it. And then we could do more questions next time about Lab 2. But Lab 3 is going to be a video game. Let me show you last year's. Let me see if I can get enough bandwidth through Wi-Fi here to show you last year's. This is very similar to what you're going to be doing. Yeah, of course, yes. Open it, sure, why not? So the balls are interacting, they're actually bouncing off of each other. They're doing hardball dynamics. The sound effects are direct memory access. We're going to have to talk about that. And part of the grade is how many balls can you animate at 15 frames per second? They did a ton of balls. Boy, is that annoying too. Wow. But this is, so back in the bad old days, this is what, 5 years ago? This is what it looked like. It was on a black and white television, boring, no color, but the dynamics was a little bit slower. So you could actually see the balls bounce off of each other.
When they're ejected, none of them should be. They have to make a collision first.
I mean, you can see the balls scattering off of each other. So part of it is to, like that one is still, and now it's being hit and it's not moving. Oh my, a little bug I didn't notice before just now. So I have to go back and change the grade, right? Yeah, right. So what you're going to do is a variant on this, which is going to be to make a hardball system, a billiard system that will be played on a court that looks like this. Oh, I can't blow it up anymore. Looks like this. So 320 by 240, the screen. You're going to draw a line around the edge. There's going to be two internal lines that are about 60 long. A paddle which you're going to be able to move using a screwdriver and a trim pot, a potentiometer. So you're going to move this up and down using the analog to digital converter. And balls are going to get fired out of this end. If they hit this side of the boundary, they bounce back. If they hit this side of the boundary, they disappear and you get a point. If they get by the paddle, you get -1 point. The goal is to come out with a positive score, which is actually rather difficult. And so the more balls you can animate, the more that are going to get fired in from this edge, the harder the game gets and the more interaction there are between balls. So ball interaction, you have to compute collisions between every two balls. Is it an n-squared problem? This turns out is non-trivial, but the computation to find out if you have to do the collision is n-squared, but in fact you don't have to collide many balls. If you sorted them, you might be able to make it n log n. Don't bother, unless you're really into the computer science side of things. But so the visual part of this is going to be adjust the paddle position to get maximum balls bounced back to one of these two locations. The sound is going to be generated. There has to be at least two sound effects, one perhaps for a miss, one for a catch, one for the end of game, one for a catch. It can be any two sound effects you want or more. And the sounds have to be generated using direct memory access. In other words, using hardware to drive the DAC so that it takes no CPU to make the sounds. No CPU, yeah, cool. So making the sounds, no matter how complicated you manage to make them, you can go, ouch, whatever it is, takes no CPU time, and you can dedicate it all to moving balls around, which is what you're going to be graded on. So we need to talk about direct memory access, how to use the analog to digital converter. So the topics for this lab are direct memory access, the analog to digital converter, dynamics, how do you actually calculate colliding balls, and overclocking. Oh, wait a minute. If you're being graded on the number of balls you can animate, how much can you overclock this CPU? How much pain? So my code has typically locked the frequency to 40 megahertz. The CPU is guaranteed to 50. Many, maybe most, run at 60. I have seen one, the first one I tried, of course, so I thought they all worked that way. I saw one that ran at 76 megahertz.
For how long?
Huh?
For how long?
Well, until that got too hot. Yeah. So they'll get warm. So I wouldn't suggest overclocking very much, but you might want to go above 50 or up to 50 at least. That'll get you another 20% of CPU. That's worth doing, and it's almost free. All you got to do is change the phase lock loops and all the timing code. But I think all my timing code scales automatically if you set the if you edit config.h. So, and the dynamics you might want to look through. It's kind of highly encoded because since this is a CDE, I put it in vector notation going back to sort of physics 1. And so this is the vector formula for updating the velocity of balls that impact. Normal integration mechanisms don't work well because when two balls hit, you go from zero force to almost infinite force and then back to zero very quickly. That means that there's a heavy discontinuity in the function, therefore in the acceleration. So we're just going to throw away the acceleration and compute conservation of momentum, which doesn't depend on the details of the interaction, just the result of the interaction. So got to go through all of that physics, which might be a little bit dusty, and dust it off. So next time, more questions on Lab 2 if you got them. Otherwise, we're going to continue on Lab 3.